All right, let's try to wrap this up here in Unit 1, Chapter 5 here. We were spiraling back through, and we were hitting on things like box plots as well, comparing data as where we were at. And I left you with this one. I said the graph below compares cumulative frequencies plotted against age for the U.S. population in 1860 and in 1980. So they were comparing them, right? So here's the cumulative data of 1860, all right, of ages, and 1980. Okay. And as looking at this, it says, how do the medians and interquartile ranges compare? So the middle, right? Well, the middle is literally 50%. So the middle of this is in 1860 happens to be around 20, and the middle in 1980, if I pull it across, we are around maybe 31, 2, 3, 4, 5, maybe 32. So the middle kind of went up, is basically what we're saying. Just look across the 0.5 on the vertical axis, and we see that in 1860, half the population was under the age of 20. All right, half the population. Whereas when we did it in 81, all the way up to age 31, maybe 32, must be indicated to encompass half the population. All right, looking across from 0.25 and 0.75, so roughly here's 0.25, which is 25%, so maybe it's around 9. And that looks around 12, 16 maybe for 25. On the vertical axis, we see that the interquartile range is around 9 and 35 for the third quartile. 75 is up here. So, yep, that looks like it's around there. So that middle 50% of the populace was between ages 9 and 35. Half the population was between 9 and 35. Right, so that's a 26-year chunk of time. Looking across the other one, that is right here, which appears to be around, what do we go with? 16, maybe? And then if we go to 75, that is the whole way over around 50-ish, right? 75, yeah. It's around 50-ish. For the third quartile, 16 that. So now the difference is around 34 years. So there is your quartile range for that. Thus, both the median and the interquartile were greater in 1980, right? The median age and the interquartile range were greater in 1980 than they were in 1860. The effects of changing units. Now, changing units, for example, from dollars to like rubles, or from miles to kilometers, is common in a world that seems to become smaller all the time, basically. It is instructive to note how measures of center and spread are affected by such changes. Adding the same constant to every value increases the mean and median. Remember, we hit on that one already, and I'm making sure you know it again. If we add the same constant to them, to every value in it, these are then also up by that constant. However, the distances between the increased values stay the same, and thus the range and standard deviation are unchanged. All right? So, the point I'm getting at is just that. Okay? It's that when you're adding stuff to it, when you're multiplying stuff to all the values, it'll change your mean and your median, but it will not change the standard deviation at all. That will stay the same, as well as the range. All right? Should still be the same. Multiplying every value by the same constant multiplies the mean, the median, the range, and the standard deviation by that constant. So keep that in mind, though. If you are multiplying, it will change the standard deviation of what that is. Okay? It changes all of those values by the same thing. One consequence is that no matter what the distribution of raw scores, the set of z-scores always has a mean of 0 and standard deviations of 1, -1, and so on, right? But note that multiplying will also change the standard deviation, okay? So keep that in mind. So if we take a look at an example, measurements of the sizes of a farm in upstate New York County yield a mean of 59.2 hectares with a standard deviation of 11.2, right? If all the measurements are converted from hectares to acres, all right, where one arc was originally the area a yoke of oxen could plow in one day, which is just nuts to think about what acres are coming from, how they originated. Acres, where 1 acre, all right, is what it's supposed to be, where 1 acre, there you go, there you go. So let's start this here again. I fixed that. If all the measurements are converted from hectares to acres, right, a hectare is a metric system, acres, where 1 acre was originally the area a yoke of oxen could plow in a day. Again, I don't understand how people can come up with this stuff, but what are the new mean and standard deviation given that 1 hectare is equal to 2.471 acres? Well, the mean is this, so if I'm multiplying it, all I have to do is multiply the mean by 2.471, which means it's now 146.3 acres. That means the new standard deviation, because I'm just multiplying that. If I'm going to multiply each item by it, then that means I'm multiplying each, instead of multiplying each item, I can just multiply the mean, I can multiply the median, and I'm going to multiply the standard deviation. So the new standard deviation would be that times that, which is 27.7 as well. And graphically, multiplying each value by a constant of 2.471 both moves and spreads out the distribution as well. Okay? Yes, lots of videos. I tried to chunk them. Yes, there's a lot of stuff, and yes, we spiraled through, but I hope that gave you some good background of Chapter 5 and Unit 1.